Here we are in part 2 of a 3-part series on trying to reproduce a benchtop style regulated high voltage power supply, similar to this Heath kit. This was very popular in the 1940s through the 1980s for working on tube equipment. So we're trying to do a solid state version of this, basically 0 to 450 volt, 100 milliamp style power supply. Now this supply could do more current at low voltages and less current at high voltages. I'd like to have something that could maybe do 50 to 100 millivolts over the entire range. So we're going to be doing a solid state power supply, high voltage. So let's look at a few of the components before we get into the nitty-gritty of the circuit. So some of the more interesting topics when you're building a high voltage regulated supply are, how big does the transformer have to be? Now I'm doing a linear power supply design. Why linear? Well, because a switching power supply, although this is the way we do things nowadays at high voltage, it's complex enough that it's beyond the scope of this kind of a channel. I want to do a classic linear design. So that means that we're going to make some DC with a conventional power supply. A conventional power supply usually uses a 75 to 100 watt transformer. You're going into a bridge or some type of rectifier circuit, a full wave, possibly a doubler, a tripler, a quadrupler, and you're making about 650 volts. Now with 600 or 650 volts, we can pretty easily do a 0 to 500 volt type supply. I'm going to be using MOSFETs for the pass device, and we'll be getting into thermal considerations. What kind of heat sinks do we need for, well, what's that worst case? 650 volts at 100 milliamps, that's 65 watts. You're expecting to do 65 watts of dissipation in a linear MOSFET pass transistor. That means you're going to need some serious heat sinking. We'll get into the thermal calculations and the thermal circuits. One of the viewers gave a tip for getting the heat out of these MOSFETs, and that is to actually attach the MOSFET directly to the heatsink. You put some of that silver grease underneath this, you nail it right to the heatsink. No insulator at all. And that gives you the lowest temperature resistance to the heatsink. That's a trick we're going to be using, but that, of course, demands that you're using insulators because the entire heatsink is going to be at 600 to 650 volts. So you don't want to come in contact with the heatsink because it's hot. And we are talking about pretty good sized heat sinks here to do 65 watts. We probably will need a fan that draws the heat, through these fins. So it's blowing through the fins. The ideal setup for any heatsink is to have the fins vertical like this, but that's not practical on our small enclosure that I'm planning on using. So the other thing that we're going to be doing is we're going to be doing some metering. We want to have either analog or digital meters on the front of the unit. Let's talk about some other practical things like the inlet. This is a very fancy inlet. This includes, full overload protection. It's got some filtering components in it. This is a deluxe IEC inlet with an onboard on-off switch. That's pretty nice. You don't have to go that far. You can use a simple cord and a switch. Somebody was talking about an off standby on switch. Off standby on switch. So this is a three position switch. Power supply inlet surge. Okay, this is power line surge. This thermistor type device is high impedance, and after the surge and current starts to flow through it, it reduces its impedance or its resistance and allows up to several amps to flow. Something like this on a linear supply is nice because remember, through your transformer, you're trying to charge up some high value capacitors through those rectifiers. So this input surge limiter is an important part of the design. Let's take a look at the enclosure. So here's a low-cost enclosure that I got on Amazon. It's nothing fancy. Dresses out the project a little bit, just some few pieces of bent steel, some plastic framing around it. The transformer does fit. That was one important consideration. Can we actually get the transformer to fit inside the case? So it's going to be tight in there. On the heatsink, did you notice how I had two devices? And again, this has got to fit in there somehow, right? Why two devices? Basically the same reason that Heathkit used two tubes as pass devices on their Heathkit PS series. If you have impedance that you're presenting for regulation, ideally you'd like to have 0 ohms, and when you hook up the load you have no loss and you have good regulation. But we all know that there is some impedance in the pass device and in the current limiting circuit, which we will go through. So if you can double up or parallel two identical circuits, it cuts everything in half. Basically, it should improve the regulation, and it should take the heat out of the device because you're splitting it between two devices. So we're going to be using a pair of MOSFETs instead of just one. Even though probably one can handle it, I think that using two and sharing the load is the way to go. So let's get into breadboarding next. What do we need to do on the breadboard? Now, the breadboard is a simplification of the circuit. It's using lower voltage, and we're going to be proving out some of the ideas we have for the power supply. We're going to be going through the follower style regulator and adding a current limiter feature to it and see how it acts. We'll be at a low voltage situation, around 160 volts, and we have 230 volts to work with a smaller transformer. So let's do this miniature regulator first, iron out all the bugs, and then we'll be ready to go to the high power version in the next video with the final product. This video is all about going through each one of the circuits and the ideas and making sure everything works right. So let's go to the bench. In order to start our breadboarding, we need a basic power supply, come up with a couple hundred volts where we can start to play with our circuits, establish the overcurrent protection, and so on. Best to do this at a fairly low voltage to start. And I had this transformer. It's like 150 volt AC transformer. It's also got a 6.3 volt winding. Very nice transformer for a small project, but it'll work okay for us. I've got heat shrink over the 6.3 volt filament winding. I got a bridge rectifier out of an old ATX power supply. These are usually 400 to 450 volt devices, so they can handle the 160 or so volts that come out of here, no problem. And then after the rectifier, we have a capacitor. I think it's a 150 or 100 microfarads at 450 volts. You'll see a 220K resistor as a bleeder. That's a safety device. Doesn't have anything to do with the circuit. It simply discharges the capacitor after we're done. Half amp fuse up front. The 2 meters are not in line. I just wanted to show that I will be metering this system when it is done. Okay, I'm going to bring my variac up slowly. Okay, we're getting DC showing up on the meter. The variac is also fused. Should get over 200. Okay, so we've got 220 volts to play with. So I could use a couple of the 82 volt Zeners, and that would establish a reference. And then we would take the potentiometer off that reference and try to control the MOSFET. So this is what I would consider to be a safe voltage to start working with. And this is our voltage on the input side of the regulator. We can do some testing to see what kind of a load this can support safely. That'll be the next test. We'll put a load on this that represents maybe, well, I don't know if we're going to get 100 milliamps, but let's see what we can get out of this transformer for DC. We're not going to do any better than that with our regulator, right? We need to know what the DC capability of this power supply is before we start. I have a 5K ohm 10 watt load on the output of our basic front end power supply. Let's bring the variac up, see if this power supply can deliver current. Okay, there's 100 volts, 20 mils draw. Okay, so 43 mils at 216 volts under load. Hey, this is a 2000 ohm load, 2K. It's a 25 watt resistor. We're going to need that because if we put out 200 volts into 2K, we're talking 20 watts, 100 milliamps. So can that transformer really deliver 20 watts? I doubt it. But let's try anyway. Let's go. Okay, we've got 25 at 50. 100 volts out. 175, 87. Wow, it just about does it. 198 at 99 milliamps. And yes, ouch, the resistor is hot. Okay, here's the prototype board built on a QRP-Me Corn QRP contest board. That's really inappropriate, but that's fine. We're just using it as a place to build the prototype circuit. So the first thing we have to do is set up the reference voltage for the regulator. The reference in this case is going to be two 82 volt Zehners. These are some old Motorola 1 watt Zehners. As you go higher in voltage with the Zehners, basically the current that you put into them reduces pretty drastically. So where you might have wanted 10 milliamps through a 12 volt Zener, you might only want 1 milliamp, 2 milliamps, 3 milliamps with an 82 volt Zener. Consult the data sheet. So I did look at the data sheet and I found out that the Zener works very well from about half a milliamp up to 3 milliamps, and it doesn't go out of regulation when you're at 5 milliamps. So that's the target. So I've selected looks like it's a 27K resistor. Let's increase the voltage until we get the Zener biased to the point where it starts to get to the knee region and we start to see some leakage current. There we go, some leakage, 127, 150 volts. It's starting to go in. Looks like we're in regulation. Okay, that's full blast. Looks like I have 2.3 milliamps. Okay, I'm going to start reducing. Okay, it's about a half a volt, right? Let's see what that voltage is. Well, 200. That's perfect. So 200 volts, it starts to fall out of regulation. And remember, 200 volts was where we were when we were taking the full 100 milliamps out of the transformer. So I would say that 27K is an ideal resistor. Now the amount of dissipation in the Zener is simply the current times the voltage. And that's well within the specification of the 1 watt Zehners. And they won't overheat at this low current. So now we have our reference established. Okay, here's the smoke test. This is just the basic regulator. Homing in on the schematic, I've made a few changes for this initial test. The current regulator is not hooked up, so we're just going to a 6K load off the output of the MOSFET. 6K is just a modest load. I'm only using 2 of the Zehners, so that's 160 volts for the reference. And I've increased the series resistor going to the MOSFET's gate to a 330K because why not? It's high impedance. Okay, let's check to see that we've got our 200 volt input. 233, that's good. And 0 output. I'm going to increase the potentiometer, the 500K pot. Here we go. Okay, I'm up to 35 volts. We're drawing 5.9 milliamps. 85 volts, 14 milliamps. About 150 volts, 24 milliamps. And here we are, 161.2 at 27 milliamps. And after I run this for a little while like this, I'll feel the MOSFET with the power off to make sure that it's not overheating. I don't expect that it is. We've got our two diodes hooked up right, or we'd have some other issues. Okay, let's try a heavier load. The MOSFET was not warm, hardly feeling that dissipation. Here's a full 2K load. And I've already brought up the potentiometer. Let's bring this up. Now we're starting to draw some current with this load. Yeah, this is better. At 100 volts, we're already drawing 50 milliamps. Okay, looks like we're topping out at 79, just about 80 milliamps at 160 volts. Looks like our regulation's excellent. Regulation's holding right up. I love that. 160 volts out. Let's let that burn in a little bit and see how hot the MOSFET gets. Off and discharged. Oh yeah, the heatsink is warm. It's not hot, just warm to the touch. So that 160 volts at 80 milliamps, we were getting some dissipation in the MOSFET. IFR BG30 is doing a good job, no problem at all. Okay, so I'm pretty confident with the regulation on this basic circuit. Now I want to try to do a current limiter. And I've got a TIP 31A transistor on there just because it was handy from the junk box. The TIP 31A is a typical NPN. It's got an HFE of about 40, which should be absolutely fine for this application. So I'm going to be adding the 6.8 ohm resistor and the 100 ohm resistor and wiring up the current limiter and see if we can get this to work. I may start with a lower current limit. We know we can deliver 80 milliamps, so let me try to set the current limit for something less, like 50 milliamps. So let's take a look at the schematic. The fast small input fuse is my wishful thinking to save the MOSFET from a catastrophic breakdown, in my prototype testing, should something go wrong. The input fuse or current limiter would definitely be too slow to save a MOSFET. R1 provides the bias current for the Zener stack. High voltage Zeners generally require less Zener current, depending on their voltage or power rating, than the typical 12 volt Zener. Consult the datasheet. R2 is the voltage control. It's of course going to steal some bias current. Usually it's less than half a milliamp, so keep that in mind. The MOSFET itself is high impedance. Q1 will simply follow the voltage on its gate within a couple of volts. See part 1 of the series to review the follower regulator theory. Power MOSFETs are rugged, but they do not like to have their gate voltage deviate too far from their source. Generally, they can tolerate input signals from plus or minus 20 to plus or minus 30 volts without destruction, depending on the device. So the 12 volt Zener from gate to source acts as a voltage clamp of 12 volts and 0.7 volts in the reverse direction. The diode across a MOSFET's drain and source internally is called the body diode or the intrinsic diode. It's not a deliberately added component, but it's an unavoidable parasitic PN junction formed by the internal connection of the MOSFET's source to its substrate. For base junction transistors or MOSFETs alike, or even for linear regulator chips like the LM117, a good quality rectifier like a 1N4007 will have a lower forward conduction voltage than the body diode. So it steals the kickback current of a high voltage inductive load or a large charge capacitor in the load before the slower body diode can turn on and possibly over-dissipate and damage the pass device. So this external diode is most important in high voltage switching systems. It acts as a built-in safety path for inductive loads like motors or relays to dissipate energy safely when the MOSFET turns off, protecting the transistor from inductive kickback.
Modern MOSFETs have eliminated this practice with improved onboard protection. For best protection and efficiency, with high-speed switching especially, you could add a proper fast recovery diode with proper PIV rating. Why don't you steal one from an ATX power supply instead of the one in 4007? So how does the current limiter work? It's pretty clever actually. R6 acts as a sense resistor. A bipolar overcurrent protection circuit for a MOSFET uses a low ohm current sense resistor to measure the load current. When the current spikes, the voltage drop across the resistor turns on the base junction transistor, which yanks the MOSFET's gate. This instantly limits or shuts off the output to protect the component. In our case, it basically brings the MOSFET into a high enough resistance condition to keep it in the safe operating area. This is at the expense of regulation, of course. Since the whole thing is floating, Q2 needs only have a modest voltage rating.
The complete breadboard along with the current limiter circuit. I've got a tip 31A in there. It's a small power transistor. And for R6, I have a 10 ohm in there. Now 10 ohms is going to restrict the current quite a bit. We have 230 volts as our input voltage available. We have 160 volts of Zener, so the maximum voltage that we can produce is 160. With this current limiter, somewhere along the line, it will limit the current and keep the voltage steady at that current. So right now I'm at 12 volts. Let's start increasing. Everything is going up as normal. Up to 50 volts, no problem. 70 volts, 80 volts, and now it's stopped. I'm turning the knob all the way, and it seems to be stuck around 95 volts and 47 milliamps. And that started to cut in. Looks like it really started to cut in around 60 volts. And we're limiting at 46 milliamps. It's shutting down the MOSFET. So that's working pretty well. Actually, 46 milliamps is not a bad value when you think about it, but this is proving principle. The circuit's working perfectly. This should go all the way to 160 volts. Instead, at 91 volts, it's current limited at 45 milliamps. Here's the fun part where we put sudden loads on the output. I have everything maximum, 161.8 volts regulated on the output. The only resistor is the 150K across the output. And I'm going to suddenly put a 1500 ohm 25 watt resistor on the output. From 160 volts, this is immediately going to ask for over 300 milliamps of current. We know the transformer really doesn't want to deliver 300 milliamps, and we know that our current limiter should probably come in and protect the circuit. Let's see if it can. Let's complete the circuit. Okay, it brought the voltage down to 75 volts, and the current limiting is at 48 milliamps. Remove the load, it goes back to 160. So the current limiter is working very nicely on this overcurrent situation. Good one. This is a 160 ohm resistor. 160 volts and 160 ohms? What does that tell you? That tells you 1 amp. So now we're going to ask 1 amp out of the power supply. Let's see if the current limiter can handle this. Brought it down to 8 volts and 50 milliamps. Again, returning to 160 when the load is removed. And finally, the one that everyone's been asking for, I short circuit. Okay, we're looking for I short circuit. This is where we actually short the output. Okay, we're fooling around and we accidentally short the output. What will happen to our poor MOSFET when the circuit is asking for, 25 amps? Or whatever a short circuit represents to this to this thing, just the resistance of the wires that are doing the shorting, I guess. Okay, here we go. Let's see if it survives. This is the coup de grace. 200 millivolts, 48 volts. It works. It passes the short circuit test. I think we have a circuit. Now we can begin to build in earnest and put this circuit into the higher voltage situation, build it right, so to speak, and start to put it in the case. So that's going to end it for this video. These are the basics that are going to allow us to build a high voltage regulated power supply that's got some short circuit protection built in.